Okay, so this next session is 4 talks in a row. So hopefully you used the bathroom or got something to eat and you're good to go. They have a common theme, and the common theme in the next 4 talks is that the numerical methods all were developed and implemented within the lab, and they were primarily the brainchild of our next speaker, who's Dr. Sainadh Talk, who's a postdoctoral researcher in the lab. And he's developed a number of what I think are world-class numerical methods in terms of their capabilities for turbulence and shock capturing for high-speed flows. And he's enabled, single-handedly, working with students in the lab, these other students, to be successful in their very challenging applications related to high-speed flows, which they're going to be talking about over the next 4 talks. So let me start by introducing Sainadh. And his title of his talk is High Resolution Numerical Methods for CFD. It's going to be a tour de force of everything he's developed in the last few years. And I'll turn it over to Sainadh now. Thank you.
So I'll just wait a few minutes so that people are coming.
30 seconds. Make sure you use your microphone if you need it.
Okay, so the title of my talk is the High Resolution Numerical Methods for CFD. So these are the numerical methods that are developed in the last 3 years as a postdoc in the CFD lab. This is the overview of the talk. So I'll give a brief introduction. Why do we need to work on the numerical methods, why they are important, and I'll briefly present the compressible Navier-Stokes equations. And I'll explain what is a discretization of viscous fluxes. We found that they are important, that people usually neglect the viscous fluxes and they say the convective fluxes are more important. You can use any scheme for the viscous fluxes, you can get the same results. But we found that it's not the case. And then I'll explain the new way that we have discretized the convective fluxes, that we say that we reuse the gradient and viscous fluxes that are already computed in the viscous fluxes, which we call the gradient-based reconstruction. And we have different ways of doing the shock capturing by using the MP limiter, etc. And then I'll give the conclusions. So, okay. For the compressible flow simulations, accurate high-speed flow simulations of practical interest require numerical methods with high resolution properties and contrasting requirements. What I mean by contrasting requirements is that, for example, you're simulating turbulent flows that you need low dissipation. That means you don't want any dissipation so that the turbulence will not be dying out. But on the other hand, if you have shock waves, you need some kind of a dissipation so that you don't get any oscillations. That's a contrasting requirement. You don't want dissipation here, but you need some kind of a dissipation here. And it gets even more complicated when you have material interfaces. That means you have 2 different gases which have different specific heat ratios and their mass fractions. And then the shock is interacting with the material interface. It becomes even more challenging. So it puts a lot of, you need numerical methods that should have low dissipation, but should also be able to capture the shock waves and still get the turbulence. So these are the compressible Navier-Stokes equations. You have here is the conservative variables, and the FCGC are the convective fluxes, and FEGV are the viscous fluxes in each coordinate direction. And you have the Q is the conservative variable vector, and the FC is the convective FC and GC are the convective fluxes and the convective fluxes. And then we have the viscous fluxes, FVGV. And in the viscous fluxes, this tau x's, the viscous stresses are computed like this: Q by 3 mu dou E by dou x minus dou V by dou x 1. The point I'm stressing on the stresses is like, okay, you have these dou U by dou x, dou V by dou y, which are the gradients, which needs to be computed when you're doing simulations. Okay, so we discretize our grid on a cell-centered grid. That means all the values are at the cell centers, this Qi, which is in the blue dot. And then you need to compute these FV and GC on these half locations, which are done by this dotted line. So which is denoted by J plus half. So you have to compute your, you have to interpolate or reconstruct your primitive variables or conservative variables to these half locations so that you can compute these F at J plus half in the X direction and the G at I plus half at in the Y direction. And then you have the source terms. And then finally, you compute your residual, which is given by this semi-discrete form. So dq by dt is 1 by delta x fcj plus half minus fcj minus half, j plus half, which is here, and the j minus half here. In the same way for the viscous fluxes. That's the way we discretize our equations. So everybody usually starts with the convective fluxes, but for change, it's taking some time to go to the next slide. Sorry. So everybody starts with the convective fluxes, but as I said in the introduction, that we found that the viscous fluxes are as important as convective fluxes. So first thing I want to explain how we discretize the viscous fluxes, the FV at J plus half. So in the one-dimensional scenario, you can say, okay, F at J plus half is tau at J plus half, and tau at J plus half times E at J plus half and Q at J plus half. So this tau at J plus half requires dou U by dou X at J plus half. So you need to compute the dou U by dou X at this J plus half location. How do we compute this dou U by dou X at J plus half is by using an approach called alpha damping approach. Which is given by this particular equation. It has two parts. One is the consistent term and the damping term. And the consistent term is like you have a du by dx, you have the gradient at this particular cell, and you have a gradient at this particular cell. You take an average, that is dou by dou x at j and dou by dou x at j plus half. And then you have what is called a damping term, which is given by this particular equation, which is u right and the u left. And this alpha is a free parameter that will decide your spectral properties, your order of accuracy, and so on and so forth. And the important point is like how you compute this dou by dou x. And this is, for here, I'm showing you the fourth order finite difference equation. You can use a sixth order one here. You can use a compact finite difference, anything. And by changing these, how you compute these gradients, you get new and different types of schemes. So the viscous fluxes, are they important? Like, does viscous fluxes discretization matter? Is it important? Like, if you read any paper in a computational fluid dynamics papers, they say, okay, I'm using a standard second order scheme or a generic sixth order scheme, but they don't usually say, like, if I'm using this particular method, this is how the scheme are discretized. They don't usually explain. So it has become a problem for me. Like, I took one particular scheme and I run the simulation, I get a different result. But in the literature, people say, no, you get the same result. You just change, you use anything, you will get the same result. But we found that that's not the case. The viscous fluxes have an effect on the solution and it can be quantified. Next. Okay, so this is a standard test case of viscous Taylor-Green vertex that everybody does to validate their codes. And it's a relatively turbulent flow simulation, and it's a standard test case. So we derived different alpha damping schemes. Here we have, this is the, so in the viscous terms, you're approximating the second derivatives, that is the dou square u by dou x squared. So if you do a Fourier analysis, this is how the exact curve looks, the black one. And then we derive three different alpha damping schemes, one, two, and three, which is having a better spectral properties. And these three, the blue curve and these green curves, are the existing schemes that are there in the literature, which we call as a non-alpha damping schemes. So what we found is that when you have a better spectral properties, you're going to get better results. And So we derived the alpha damping schemes with superior spectral properties, and then we compared with the existing schemes, which are we call non-alpha damping schemes, which are these two, which doesn't have this high frequency damping properties. And again, we want to, how do we quantify the effect of the viscous fluxes? So we have the convective part and the viscous part, right? So, but if you use an upwind schemes, there are central schemes and upwind scheme in the convective terms. But if you use an upwind scheme, which will have a dissipation, and you'll not be able to measure how the viscous fluxes are having an effect on the solution. So we choose what is called a kinetic energy preserving and kinetic energy and entropy preserving schemes. That means there are the central schemes and they are stable and they don't have any dissipation. By using that approach, we can quantify how the viscous fluxes have an effect on the solution. So we did the simulations for the Taylor-Green vertex by using a 9th order upwind scheme. And for all the, and this is the entropy for the viscous Taylor-Green vertex. And this black curve is by using the direct numerical simulation on a 512 cube grid. And by using an upwind 9th order scheme, all the viscous schemes that I've shown in the previous slide, all the viscous schemes that I've shown in this slide are performing exactly the same. There is no difference at all. But the kinetic energy is completely going to zero and it is not preserving, unlike the kinetic energy preserving schemes. So if you use the kinetic energy preserving schemes, these non-alpha damping schemes, which doesn't have the high frequency damping properties, or are over predicting the entropy or even on the Corsi grid, which is impossible. Like DNS is saying this is how much the entropy should be, but these non-alpha damping schemes are over predicting the DNS data, which is unphysical. But on the other hand, the alpha damping schemes are able to correctly predict the physics more appropriately. They're all within the DNS, which is physically correct. So now we can say these viscous fluxes have an effect on the solution and they have to be taken care of. So the important property that a viscous scheme should have, this, what is this called, as a high frequency damping. All the schemes that are going down are over predicting the DNS data, but the schemes that are having this damping properties are giving a physically correct solution. So as I said, the pool schemes are over predicting the DNS data and the alpha damping are giving physically correct solution. Okay, fine, but everybody is saying the viscous schemes doesn't have any effect. But we also have to show that, yeah, there are other people in the literature who are showing similar kind of results. And we found that by using a non-dissipative discontinuous Galeckian methods by Tohoku University, they are also showing, like, if you use a non-dissipative convective flux discretization, it is over predicting the DNS data. All these schemes are over predicting the DNS data. And in the appendix of their paper, they said, like, it can be attributed to the viscous flux discretization, but they didn't say like how it could be possible to overcome this. So the conclusions of the first part is like, if you use an upwind scheme, you will not see any effect on the viscous flux discretization. But if you use a non-dissipative scheme, you can see how the viscous fluxes are having an effect on the flow simulation. And the important point is, like, if you have the viscous flux discretization should have good spectral properties, and it should not be neglected at all. So that's the first part of the talk. So now I come to the convective fluxes. I want to do the spatial discretization of the convective fluxes. And I said the spectral properties of the viscous fluxes are more important than mere order of accuracy. And I said, okay, this is how I'm computing the dou U by dou x at j plus r. I have a consistent term and a damping term. And the dou U by dou x is computed by using this particular formula. We can use any other finite difference method, like the 6th order or the compact schemes of LLA, etc. Now, the key question is, okay, I have these gradients. I'm computing these gradients. Can I reuse them anywhere else? Okay, I have these dou U by dou x, dou t by dou x, all those things. Can I use them? Because it'll be efficient. I compute them once and I use them in so many places. So how do I reuse them in the convective fluxes? So in the previous slides, I talked about the viscous fluxes. Now I explained about the convective fluxes. In general, for all the upwind schemes, for the convective fluxes, we use what is called a Riemann solver. And it has a physical central flux and a numerical dissipation, which is called U right minus U left. So the objective of the convective fluxes is to find out the left and right states, U left and U right, at the cell boundaries. That is, U left at I plus half and U right at I plus half. It needs to be found. So we have a general formulation for these to finding out these values at U left and U right, which is given by this Legendre polynomial. If you know CFD numerical methods, there's a scheme called Muzzle scheme, which is given by Professor Van Leer in 1977. He gave this formula for a Legendre basis, and it is given by this Uj at cell center, U dash, that is the gradients, and this is the U double dash at the second derivatives. And then if you simplify it by setting the x equal to xj plus delta x by 2, you get this simplified forms. U left is uj plus half d by dx and the second derivatives. So the gradients that I'm using in the viscous fluxes in the past, I'm using them again in this particular equation. So I compute the gradients for the viscous fluxes, but I'm also going to reuse them again here. So it can be either explicitly computed by using the sixth order formula, or they can be computed by using an implicit scheme, that is a compact scheme, which you require a tridiagonal algorithm to invert and find out the gradients. And the second derivative, this d square u by dx square, can be expressed in terms of the gradients at the cell centers and the gradients at and the values at the cell centers. So that's how you get this, what is called gradient-based reconstruction. So U left is given by this formula, and the first derivatives can be computed by using any of the finite difference method, and then you compute the second derivatives, which you get the final formula. So in this picture, I'm showing the dispersion and dissipation properties. If you're computing the sixth order explicit gradients, your dispersion is, you're able to capture this many waves. And then if you're computing implicitly, that is the compact schemes, you get a much better dispersion. So what is the advantage? So as I said, you compute once and use it several places, so it becomes extremely efficient. All the schemes that we have derived are fourth order schemes, but the implicit scheme, which is given by this green curve, is giving much better results than the explicit scheme. So because the dispersion properties of the compact scheme are much better than the explicit scheme, so that is why it is able to give much better results than the explicit. Even though both the schemes are fourth order accurate, because one of them is having a better dispersion property, it is giving much better results. That is one of the things that we have wrote in our papers. Like you just don't have to worry about the order of accuracy. You have to have a good spectral properties. So once you computed the velocity gradients, they're used in viscid fluxes, they're used in viscous fluxes. You can also use them in post-processing quantities. Like you want to compute the entropy, the gradients are used. You want to compute the density Schlittern, you have the gradients already available. You want to identify the shocklets in your mixing layers, they're already available. I have seen papers where people compute the gradients to identify the shocklets in their mixing layers. So that's also can be used. So you compute once and use them in several places. This is quite different from what other people have done in the literature. This is why it's an efficient method. So far, I'm showing only for the simple cases, the cases where there are no shock waves. But in this case, we have to deal with shock waves and other things. And we use what is called the monotonicity preserving approach of Schurich and Kuhn. And the resulting schemes are called MIG or MEG, which is monotonicity preserving explicit or implicit gradients. And we compared our results with the Tino scheme, which is one of the popular variants of the Wiener scheme in the literature. And you can see the results for the 1D test cases. And the blue dots are given by the Tino scheme, which is not able to preserve the high frequency regions, but the explicit and implicit gradient methods are able to capture these high frequency regions without any issue. Next slide.
I think there are too many windows open, I was told by a little birdie, so I need to fix that for the next.
Okay. Those are the 1D test cases. Now I'm going to show for the viscous shock tube test case, which is a square shock tube with insulated walls. So the shock wave is going in this direction and it hits this wall and comes back and it interacts with this bond layer and it's going to give a complex patterns. And we did the simulations with our method and the Tino scheme. And this is the reference solution on a grid size of 4,000 by 2,000. And these two are simulations on a smaller grid size like 1280 by 640. And the mixed scheme is as good as the reference solution, even on the smaller grid itself, compared to the Tino scheme. And we also carried out the simulations for the multi-component flows. And this is the test case for the compressible triple point. So you can see all the schemes are giving without any oscillations and so on. But if you look at this contact discontinuity here, the Tino scheme is having a much thicker line. That means it has more numerical dissipation or numerical diffusion. But if you look at the mixed scheme, the contact discontinuities are much more thinner. And that means the numerical diffusion is much lower. It's the same case with even for the long time simulations. We are able to get much better vertical structures, and also the contact discontinuities are much thinner. And finally, we have in these cases, these are standard test cases, but we want to do next slide. Okay. We want to do shocks and turbulent flow simulations. And the MP criteria that I have shown in the previous slides is too dissipative. It gets activated too much and it might kill the turbulence. So we use the Ducrot sensor, but we know the Ducrot sensor cannot detect the contact discontinuities. So to overcome that issue, we have what is called a selective sensor approach, because we know that the second wave in the Euler equations is the entropy wave, which means we can, if you use a sensor that can detect the contact discontinuities, we apply the Ducrot sensor for 1, 2, 3, and 4, 1, 3, 4, and 5 waves, and the contact discontinuity sensor for the second wave. Then we are able to capture even the contact discontinuity, and we still do the turbulent flow simulations. And this is for the inversive Taylor green vortex. And again, the Tino scheme is not able to capture the small scale structures, but the selective sensor is able to capture all these waves, and which is much better than the MP scheme. And even for higher Reynolds numbers of RE 2500. And so we propose a novel way of computing cell interface values by using gradients. You compute the gradients and you use them wherever you want, so that it becomes efficient. And not only efficient, you can see that the results are better than the Tino scheme and the Vino scheme in the literature. And next slide. So far I've talked only about the benchmark test cases. In the next talks, Nathan Hoffman is going to explain how these methods are used for the hypersonic cases. Hemant is going to explain for the acoustic simulations, and Sean is going to talk about his scramjet simulations. Thank you.
Thank you. We're going to take some questions, and I'm going to shut some of these windows here because we think that that's causing the problem with the delay. So, any questions for Sainadh?
Yes.
Please go right ahead. Oops. Okay. Please, question? Yes.
Does it matter when you're reconstructing implicit flux? Does it matter where you're reconstructing to primitive or conservative? What difference does it make?
It makes a lot of difference. It depends on the problem. If we usually saw that if you do a primitive variables, it has more dissipation. But if you're doing multi-species simulations, the algorithms always use primitive variable reconstruction. But if you're doing single species, you can choose either primitive or conservative. But we found that the conservative ones are less dissipative.
Okay, any other questions for Sainadh? Okay, if not, let's thank you very much for.